laser facilities, laser plasmas, and diagnostics. This presentation will start by introducing what a laser is. It will then describe two of the large laser facilities in operation at this time. There will be a brief discussion of laser-produced plasma, and to finish off, some details of diagnostics used will be given. What are lasers? Laser stands for light amplification by stimulated emission of radiation. Lasers are concentrated beams of electromagnetic radiation, light, travelling in a particular direction. The defining properties of laser light are that the light waves are coherent, all travelling in harmony with one another, and that they are usually of one wavelength or colour. By harnessing these properties in a device that reflects light back and forth through a special material, it is possible to generate an amplified light source, or laser. Lasers range in size from microscopic lasers, on the right, to massive lasers used for inertial confinement fusion, nuclear weapons research, and other high energy density physics experiments, seen here on the left. There are a number that will fall between these two extremes. The National Emission Facility, seen from above in the figure on the left, is the world's largest laser, with 192 laser beams. NIF is capable of directing nearly 2 million joules of ultraviolet laser energy in billionth of a second pulses to the target chamber centre, seen in the middle diagram. When all that energy slams into millimetre-sized targets, seen on the right, it can create temperatures of more than 100 million degrees and pressures more than 100 billion times Earth's atmosphere. These conditions are similar to those in the stars and the cores of giant planets, or in nuclear weapons. The new Orion facility at AWE has 12 high-powered laser beams capable of heating and compressing material to very high temperatures in a fraction of a second. Physicists at AWE will be able to obtain crucial data about how the components of their aging nuclear weapons behave. Each of the 10 long-pulse lasers can deliver 500 joules of energy in about a nanosecond. There are also 2 short-pulse lasers which can deliver the same 500 joules of energy in just half a picosecond. Orion's main mission is of a similar field to that of the NIF, and is to explore how nuclear weapons work as they age. Almost all detectable matter in the universe is in the plasma state. Plasmas are made at high temperatures when electrons are stripped from neutral atoms. Their constituent parts are freely moving ions and free electrons. They are often called the fourth state of matter because of their unique physical properties distinguishing them from solids, liquids and gases. The figure shows characteristics of typical plasmas. Solids, liquids and gases are found at the bottom right of the diagram. The capabilities of NIF will allow production of hot dense plasmas that can be characterized in great detail. NIF will allow measurement of such properties as electron and ion temperatures, charge states, electron density and plasma flow velocities, all of which are essential for understanding experiments in plasma physics. Diagnosing NIF experiments requires detection of different types of emissions, such as X-ray, neutron and optical. These various systems can be seen by this schematic. To give a more detailed example of a particular diagnostic, we have an X-ray spectrometer named HENIX. This was a core diagnostic designed for use at NIF. It can record X-ray spectra in the region of 1 to 20 kiloelectron volts. This is done by 2 methods. 4 reflection crystals cover the lower energies, and 1 transmission crystal covers the high energies. The left figure shows 2 reflection crystals and the path of the X-rays into the detector. The centre picture is the entire instrument with the key components labelled, and on the right is an example spectra obtained from the spectrometer. To summarise, these topics have been very briefly introduced, and it is hoped that an insight into this area of physics has been provided.